Can you hear me?
Okay,
Can you see my
Yes, we can.
screen?
let,
All right,
let
perfect.
me
Thank
just
you
open
so
the
much.
camera so you see our audience.
All right. So I have a really bad throat, and this is the reason. I've actually done 7 keynotes in 4 continents this month, so I sound really funny. But I hope, if this doesn't go well, I'll send you a recording of another one of the keynotes. But I'm really excited to get started. This is my first time doing a keynote in your country, so it's extremely exciting for me. I just wanted to show you an app before we get started, and how quickly this app works. This is running out of one server. It's just one test server. And as you notice, I don't have to tab out or anything. I can even come and type if I wanted to. Let's say I said 23.45. You see how these sliders automatically change? And this updates very, very quickly. And the amount of data that's coming back is quite a bit. So you see there's a lot of calculations happening in the background. There's data. If I were to inspect this, since we're developers, let's look at this as what's my network call look like. All right, so in this case, you'll notice I only have 45 milliseconds for that call. Very, very quick. 62 milliseconds, 201, extremely quick, right? And that's amazing because we're going all the way to the back end, coming back, and still I'm not even hitting half a second. And visual details, there's a lot of different ways I can show you this, but in short, you see how you can see a lot of this visualization and everything. So I have graphs, I have a database, I have an API, I have security, I have a UI, and it renders extremely fast. So today's talk is really going to be about showing you techniques I've learned in my last 20 years of coding and architecting applications that can make your applications way faster. And it's really not about the hardware. You see, there's only one server. It's a test server. It's running out of Azure. Now that said, I want to show you an example. I am going to run this, and you see how this thing keeps moving. It took about 2 seconds or something. And here, this goes extremely fast. You don't even see the flick. So since you're developers, let me show you how Inspect tab works. You all have used this, so you know if there is something in the console, you will see it right here. I'm run this again. Takes a while. Oh, it gets printed. It takes about almost 2 seconds. As you can see, the time taken is 1775 milliseconds. And this one is nothing, not even 1 millisecond. It's 0.99. That's like 0.01. Oh, sorry, 0.1 milliseconds. That's extremely fast. You see, it says 0 milliseconds. I run this again. It gives you the same exact 1700. And now look at that. The value is still the same. You got the same answer. Except the difference is this was called millions of times, and this is only called 39 times. So this is exactly what the power of an algorithm is. And if I were to show you this in page source, you can see this is a very simple function, calculating Fibonacci of 40, which is nothing. And if n is 0, the return is 0. If n is 1, return is 1. Otherwise, the return is the last two values, right? So let's say you have 1, 1 plus 1 is 2. That's Fibonacci sequence. Now you have 2, so 2 plus 1 is 3. Then you have 2 plus 3 is 5. And you keep going, and that's how Fibonacci sequence ends up being. So it's a very simple problem, but if you're going to waste almost 2 seconds on the UI doing this, I mean, that's definitely not good because your user will be waiting just on the UI. Think about that. And here, if you were to look at the entire screen I showed you earlier, we're getting every single response back in less than 100 seconds mostly, and in a couple of cases, maybe 200 milliseconds. And this alone, on the UI alone, this is not even taking a call to the backend, takes that much longer, right? So let's get started. Here's some information about me. I am no different than a lot of you are. I started very, very small, and then I got to where I got to. But in one thing I like to tell people is that I didn't have money for a computer. I used to write code on paper, and I did that for many, many, many years before I bought a computer. Actually, for 12 years before I even bought a computer. So things are very different now. If I can do it, anyone can do it. One of my favorite authors, Steve Souders, he says, great developers know why things work. So if you understand why things work, then you can do a lot of things that most people may not understand. A lot of people understand, oh, I can use this API. They know how things work. But if you know the whys, you can do really well. So let's talk about the first part, which is going to be the UI best practices. FT.com decided to intentionally delay their application. And when they did, they realized that a lot of users, left them in just 7 days. Look at those numbers. I mean, if it is 3 seconds slower, about 7% users left them, and that's the same on 28 days. But if 1 second slower, that alone is making them lose how many people? 5% users, and that's a lot. Just by being 1 second slower, you can lose 5% users, and that's 5% of your revenue. Now look at that. If you were on a tablet, quite surprisingly, oh my gosh, 18% users lost with 1 second. For some reason, tablet users leave you pretty quickly. Isn't that interesting? Because desktop, not that bad and interesting. Interesting numbers. Mobile also 9% in 3 seconds. So how does it work? Well, a lot of times you go to the website, takes forever, that nothing loads, and then something loads, and then the whole thing loads. Is that better, or here with nothing loaded, a little bit more loaded, and that loaded? In fact, everyone will say that one is better because you got the website in 3 seconds. Well, next one, same on mobile. That one will win. However, what if I change this a little bit to say, look, nothing loads, everything loads in 3 seconds, whereas this one, we had progressive loading, progressive rendering, and finally it loads in 3.2 seconds. You'll be surprised, most people like the one on top because no one likes to see blank pages for the first 2 seconds. So one of the best books you can read is on web performance by Steve Souders, and he teaches a lot of things, except when he wrote the book, it was HTTP 1.1, but it does help you understand the history of how things work on the browser, and that can help you. Everything he says is great, except towards the end, he says put scripts to the bottom, which I agree with, except what we also do is we put critical scripts at the top. And there's a reason. When you go to google.com, there's really not much on the page. You only care about the search to run, and that should be running pretty quickly. If that took forever waiting for the entire page to load, you're going to be frustrated. So probably putting critical scripts at the top is a very good idea. And then, of course, these are 14 rules of web performance he created. I highly recommend reading them. We're not going to cover those because, like I said, they're more on HTTP 1.1. One of the things to understand is how much time we take to reach Windows limit. It's basically, if let's say you have a round trip time from two cities, let's say from Lebanon to the United States, right? Let's say 42 milliseconds. That's not true, not going to happen, but just making it up. And let's say you had 10x segments. In that case, what's going to happen is you will take about 160 milliseconds to get the data over to me for the first time. But it's actually a little more complicated than that in real life. So what happens is the browser is going to send a synchronization, and then the server is going to send the acknowledgement. That's going to happen in the round trip time. Then the request is going to come in. Server may take 50 millisecond processing request. That's extremely fast. I'm just putting it out there for example purposes. But then, as you notice, if it's 10x segments, the max I'm allowed to send as a server is 14,600 bytes, which is 14 kilobytes. That's it, nothing more than that. So now what I'm going to get back from here, and then I'm going to make a call next time, I can double this number. So double of 14,000, 29,200. And then the double of 29,200 is 58,400. So by the time I send back, as you notice, it's about 116,000, 800 bytes. It's basically going to take about 240 milliseconds. So that's a lot. It takes a lot of time just the first time to make that happen. So what you have to understand is that if you have TCP fast open, it's going to be faster. If you have TCP slow start, it's going to start like that, and it's going to start again whenever you go idle. So that's a bad idea. what you may want to do is keep TCP fast open always. Have you heard of the critical rendering path? Well, in short, you know HTML. HTML creates the document object model. We call it DOM. CSS creates CSS object model, which is CSS OM. And then you have JavaScript. Now, JavaScript, interestingly, is blocking. Why does it block? The reason it blocks is because JavaScript has the ability to change HTML as well as CSS. Effectively, it renders the entire tree. So this is where the operation is getting expensive. So let's say you had a very simple HTML file, something like this. You start downloading and it downloads all the way till here. You should see a title. Now there's nothing like a title, so you won't see anything. And then when you download the entire file, you'll see the entire page rendered. The thing about this page is it has got a style display none, so nothing will render. But that's how HTML renders the DOM. However, the browsers, the way they look at it, they take this tree. They've got this tree. It says div is hello world, and then paragraph is hidden. And then they do their math on it and basically create a render tree. In the render tree, there won't be a p tag because it's actually hidden in the DOM. So you will see that render tree is more important than the DOM because what matters is what the browser is going to render. So you'll see a hello world right there. So tips, you can definitely use server-side rendering. You can do progressive rendering. You can also make sure that your critical CSS is inline. But let's talk about the most important part, which is the render tree, layout, and paint, because this is the most expensive operation a browser has to do. Before we get there, I just want to show you this. If you use async, then it's going to get downloaded in parallel on its own time. It's not going to block anything. It's only going to execute when it's ready. But if you don't use async, it blocks, parses, and executes. So you see there's two things that happen before execution, which is block, parse, and then execute. And that is interesting because you don't want to do that unless it's a critical script. Otherwise, it's going to block your entire download from happening while this is downloading, parsing, and executing. Older browsers, they used to do it this way. They download the script, which will basically download, and then it's blocking everything, and it's parsing and then executing right here. Then you have the second script downloading and then parsing and executing, and then you could download other things that were there. Quite interestingly, they improved. They understood how to do parallel downloads, but it's still have to parse and execute, and then other resources can download. So one of the things you can always do is create optimization. For example, Gmail on mobile, they realized that most of their users on mobile phone on a browser only used their reading app, so the app for reading. So you had all these emails, they would go read, and then they would barely do compose. If they had to respond, they'll reply to that email, but they would very rarely use compose. So what Gmail team did was the compose code was commented. Why did they comment it? Because they don't want you to spend time parsing and executing code you may not use. That's a performance benefit. So then what happens if they do compose? Well, whenever they do compose, they have a two-step operation. First step is uncomment JavaScript code. And the second step is eval, run the eval. Now, dynamically, you did it, and it's only going to cost you a little bit of performance one time, and it's still going to run the same way as it was earlier. So that's how they go around this problem, and they make their things really fast. If you use Google, Gmail Mobile, it's incredibly fast, and we can learn a lot from them, and we've applied a lot of these in our own applications. So always try to use async where you can, and not everything is going to be async, but if some things are async, definitely use it. Avoid document.write because it's going to block everything. And then defer everything except critical scripts towards the end of the body tag, like we said earlier. So now let's talk about layout and paint. Everyone's heard of frames per second. 60 frames in 1 second means we have 1,000 milliseconds to render a frame. That means we have about 16.67 milliseconds to render a frame. Not necessarily true because The browser needs another 4 to 5 milliseconds. So we have about 10 or 11 milliseconds. Now, is everyone familiar with a frame? As you can see, there are 4 things in a frame. So whenever a frame executes, you have code, garbage collection, layout, and paint. And when does a layout update happen? Layout really is calculations of changes on the page. So for example, you resize a window, you add, let's say, a detailed page. Now you have a lot of nodes. You remove nodes. You went and you had a to-do application and you deleted some of those nodes, and then you delete the reminders, so you're removing nodes. So layout is going to change, and your page will be re-rendered. And then, of course, you change any styles, like you add a background color, you add a border or whatever. That will also change your, backend. And not the backend, I mean the layout, which basically means triggering a paint. So now most people, when they read a textbook, they think it's going to work like this: code, GC, layout, paint. In real life, it depends on how you code. So if you use the for loop that keeps changing styles, elements, then what's going to happen is it's going to be code, layout, code, layout, code, layout, every single line. And over a period of time, you will go beyond the 11 milliseconds you have, and then the browser needs the time, and then you will effectively drop the frame. And finally, paint is triggered. You do not want to drop the frames. So layout is calculations pretty much, and then you have to apply those visual styles. That's when it becomes paint. So you have to create the bitmap and pixelate the screen. So things to note, right? If you can only update a certain portion of your website, then that's a great idea, because then you don't have to paint necessarily. So for example, here you'll see that if you do this, one change, second change, third change, you triggered reflow, which means you triggered paint 3 times. Whereas if you do something like this, you will trigger paint once. So this is a performance optimization. If you add something like this and you use the same element and the property from that particular entity, well, it's inefficient because you're now changing that or accessing it. Whereas if you just use a local variable, this is much faster. So paint is very expensive. You change anything, it's going to change any layout changes, pretty much triggers change, right? I mean, the paint. And that's something you need to reduce. So one way to do that is by repainting. That's actually smarter and faster compared to reflow. So how does that work? Well, first, let's talk about reflow. We talked about resizing the windows. That will change because the entire canvas is going to be re-rendered. And then you change a font type, you change a pseudo class, you change any class, CSS class attribute, or calculate the offset width or height, or modify any other style attribute of any element. That's a lot of things. So it's expensive. Why is it expensive? Because it re-renders the page pretty much, right? And which is not a good idea. So there are 3 very, very good techniques you can use. I'm pretty sure when you go to your company, they're going to love it, because a lot of senior developers do not know these techniques. These techniques are some things we've been using for a long time, and they work. So let's say you want to do a lot of operations, create a big layout, and create an element. The best way to do that is create a document fragment, and then make all the operations happen on it, and then add it here. This is the only time paint will trigger, because this is all happening in the document fragment. This is one way. If you don't like that, you can actually take an object, clone it. Now it's in memory, do all the operations in memory, create that object, and just replace the original object with cloned object. Done. You're good to go. And if you think all of that was hard, very simple. Take any element you want to make changes in, display none. Make sure it's not visible on the DOM anymore, so render tree does not have it. And then make all the changes, and then display block means show it again. So that is a very, very cool way of doing things. Thought leaders, there's a lot to follow there. Books, there's some books here. And then let's talk about scalability best practices. Sorry, I hope I had a better throat. I really sound like someone very, very different. I don't know this man that is talking today. Amazon claims that if you just increase 100 milliseconds on their response times, they'll cost them 1% in sales. That's billions of dollars. Google thinks that half a second increase in latency causes their traffic to drop by a fifth. And that's the slide that changed my life. Now, I saw it many years ago and I said, wow, we got to do things extremely fast. And that is incredible because just half a second can cause Google to lose billions. So how fast they have to be? They're so high on performance, and we can learn from them. So what are we going to do today? We're going to propose an architecture, find all the faults in that architecture, and then apply a better solution. And I'm going to keep repeating it in a loop. So one of the things you'll notice is when you do services-oriented architecture, you decided you can scale the web app, and then you wanted to scale the services. And let's say you have a service. Let's say you're on a checkout page. You want to check out on e-commerce. And now you go, oh, you know what? I want to buy all these items and I want to check out. So what services are you using? Service number one, you have to have the product services so you can get all the products. Number two, you have the order service. And then you have, taxation service, inventory service, customer details, payment service, and a lot of these services. And that's a lot of services. And if you have to make a join of them, you were better off doing that in a database if this is an RDBMS, which is more like a SQL Server or Postgres or Oracle or MySQL or something similar. Now, if that is an RDBMS, you're better off doing the join here. Otherwise, you're going to collect all of this info and do a join somewhere here. That's going to slow you down. So it's an unfortunate solution. This cannot scale until you scale this. So one of the things that Gilbert and Lynch white paper teaches is, let's say I'm in the United States, and that's network number one. Your network is Lebanon, and I've got that here, right? Now, name changes, and I want to make a change. That data has to be in both the places. So I send an update message, and it changes my name over there. So now I have data in both the places, and I'm like, great, okay, that works. Except, there's a big ocean in between, and sometimes the message doesn't go through. So now we have data that is not concurrent, and basically this is data that is not consistent with the actual data. So that's where CAP theorem comes in, which basically talks about any database can give you 2 out of the 3, but not all the 3. So let's say you're a SQL Server, it's going to give you consistency and availability, but not the best one to partition. But if you have something like MongoDB, it's great on availability and partitioning, but eventually consistent. So one of the other things that you got to understand is your system should be able to scale in a way that even if, out of 100 servers, let's say, 97 servers died, you should still be able to respond with a correct response. And that's pretty impressive. Like, for example, Netflix, they do that. They try to, render some of these servers unusable in production to see if they're scaling well. Read this article if you have time. If you already have, then you can ignore this, but one of the best articles to understand distributed programming. And a lot of people are like, why is scalability important? Well, Twitter's got 400 billion tweets per year, and Facebook's got 3 billion active monthly users a month, and that's a lot, and things are going bigger and bigger. If you don't understand scalability, what happened to Instagram can happen to you, which they were down on the launch day. So anyways, how does it start? We're a startup. We have money for one server. We buy the server. We have app server, database server, every single thing. And then it scales. Then you have vertical scaling. And you throw more RAM and CPU. And of course, that's fine. But after some time, you still understand that if your web server dies, then your app is dead. And if your database server dies, same can happen. So your app doesn't scale. Another thing to understand is if you have an RDBMS, which is a relational database, after some time, when the volume of data increases, you get no benefit in performance. Performance actually goes down, and after some time, you have no more performance benefits. Whereas a NoSQL can scale. Does that mean you only use NoSQL? No. That's not what I'm saying. You have to use both wherever it makes sense. There's no either or. So here's a good example. Key value pair. A key value pair has nothing but, like one functionality. It does good for caching. But look at that scale and performance. It's the best. And databases have a lot of functionality, but in scale and performance, they're the lowest. And then you have MongoDB, Cosmos DB, right, Cassandra, and all document databases. They're somewhere here, pretty good on functionality and pretty good on performance. And you have search engines somewhere here, a little less functionality, but even better performance sometimes. So this is a good graph you can use whenever you're designing a system. We end up using key value pairs and column family and search engine as well as others, whatever it makes sense. So after some time we go, we got more money. What do we do? All right, we'll get another server, put app server there and DB server there. Still, they're both single points of failure. What's next? Well, we decided to scale this part again. And instead of media services, which are basically monolith, we decided to do microservices. So understand that even though you can scale this part, this is not scalable, and that's not scalable because they're single points of failure. However, this is a better solution. Let's say you're YouTube. If I said media service, that would have had video, audio, thumbnails, pictures, all of that in there. Whereas now you can have video service, picture service, thumbnail service, and others, and they can independently scale. For example, if you're on YouTube, most people want to watch the video, and there's a lot of thumbnails, so you have to scale them. But there's only like 20, 30, 40, 50 pictures. There's a finite number. You can have that pictures coming out of a CDN, if that's okay with you. If not, well, picture service, but you don't need to scale this as much, but others can scale more. So that's an advantage. A disadvantage of a monolith service is, in case of a monolith, this is a monolith, by the way, you have to have the same shared packages. Whereas with a microservice, you don't have to have that. In fact, video service can use a text parser, which is V1. If you're running AI here, and audio service can use a text parser, which is version 2, no problem. It could also be in different languages. And of course, it scales, and you can have any client targeting them if you have the right API, gateway, API, and your credentials and security, you're good to go. So sticky sessions, I'm going to skip that because that doesn't really scale. But in short, you can have, in order for your sessions and caching, you can have a scalable session store. And also, load balancer can be scaled by using active-active or active-passive. Now let's talk about caching. One of the problems when we see people doing caching is how they do it. So let's say you had a version 1, you update a request. Now, load balancer makes a request, to server number 1. It goes to database, and database basically gets the data, and it actually sends it back to load balancer, except it also keeps a copy, calls it version 1 of that data, and it keeps that copy where? On the web server. The idea is next time the person makes a request, we can just send it from the cache. We don't need to go to the web server. Well, what happens if there's a new request, which basically updates that data to server number 3? So now server number 3 will have the latest, but server number 1 won't. What if the next user goes to server number 1? Well, we're in a bad spot because we have old data, right? Now, if the data is old, then what can we do? Well, maybe we can go back to the database and see if the data is old or new. Well, that defeats the purpose of having a cache because now we're slowing ourselves down anyway, so we're better off with the database. So this doesn't work, and the best way to make this work is use shared cache agent like Redis or Memcached, and you can get your data back from there pretty quickly. And now you don't have to worry about scaling because this is an auto scale caching engine. Then you have vertical partitioning, which basically in simple terms means you'll take the database and you can't scale it enough, so you add a storage area network which scales it vertically. That still makes it a single point of failure, not a very good idea. So really your challenge is, how do you scale an RDBMS, which was not meant to scale? That wasn't really designed to scale. Now, unless you're using SQL Azure, right? That's a different story. You have Microsoft's Azure backing you, so you can scale. That's easy. But let's just say you try to do replicas. Well, replicas will only, technically give you replication of your data, but doesn't really partition your data. That has nothing to do with it. Number 2, what you can do is change your data structure to be something like this, we're going to take all the social data, put it in DB cluster 1. I would have put it in a NoSQL, but a lot of people would do that in SQL because they like SQL. The problem with this is DB cluster 2 has a lot of critical data. What if you have to do a join in between? If you do a join in between, well, now the join is going to get a little messed up. It's going to be very, very slow. Why? Because it's a join between two different clusters. And if you've done SQL programming, you know join between two SQL servers is also not a very good idea, but this is actually a completely different cluster. That's even slower. Then they go, okay, you know what? I could do it differently. I could put all my first 100 clients in a different cluster and the second 100 clients in a completely different cluster, right? So the problem with this is that, fine, but what if those clients have something in common down the line? What if one company buys another company and things like that? You see, the issue is that this won't scale either. And business changes, requirements change, it happens all the time. It may scale for a very particular use case, but if your use case changes down the line, it's not going to scale. A lot of people come to you, we've been doing it for 10 years. And then you look at their application and go, oh, wait a minute, you're loading everything in 20, seconds sometimes. What are you doing? I mean, sometimes they're loading things in 5 or 6 seconds. That's really, really, really slow in today's world. So to understand this, how they think they can scale it, and then they will eventually get into sets, because after some time, what do? You don't have DB clusters, right? So what do you have? You have sets, and this is what you end up doing. So finally, you've got this diagram, which basically can help you scale every single application you ever built, and it works for us. It's been working out for a long while, and we keep changing and making it better as we go. First thing, we use a scalable caching engine, something like Redis, which is going to scale automatically. Number two, anything to do with searches. Let's say you're e-commerce and you want to search, what do you want to buy? The first thing is a search database. And then, of course, after that, you have on this side every single thing you need for your data. For example, all the comments. You're buying a product, the product has 5,000 comments. They need to be in an auto scale document database, which is something like MongoDB, or something like, what I would say is Cosmos or whatever, right? So this is basically important. Why is this important? Because this is where most of your data would be. Your goal would to put 90% of your data here, right? And this is where all your searches are coming in. So anything you want to boost, let's say you're buying a 24-inch monitor, and the 27-inch monitors on sale. I mean, the best thing is to use this, which is a search database, because it can do boosting, relevancy scores, and all of those things, ranking algorithms, things that a database is not very good at. And remember, right, retrievals are fast here. They're very, very fast. The retrievals are fast here. A database is great for ACID, but not retrievals. And that's one thing you got to keep in mind, right? ACID, as in atomicity, consistency, integrity, and durability. So that's great. So for all my employee data, all the customer data, and anything that's important goes in here. So what's our goal? Our goal is for this database to be never get from one server to even two servers by reducing the amount of data that belongs in here, because most of the heavy lifting is done by this page, this caching engine, which scales automatically, the document database, which scales automatically, and search database, which scales automatically. And we know that this scales because we have active, passive load balancer in this case. And this is anyways horizontal scale. So everything here scales. The only thing that does not scale is this, which we don't really care about, because eventually what we're saying is this isn't really something we're worried about, because we would never have that much data here. And of course, then you have the cloud option. And finally, offline processing. If you can process something offline, I highly encourage you to do that. Let's say you go to Amazon.com, you place an order. Amazon says, all right, here's your order ID, you're good to go. What I've noticed is that in the last 10 years or more of shopping with Amazon, even though sometimes my payment is not correct, they don't really tell me at that time. They do it offline, which is good, because in 10 years, that's happened twice maybe. But it saves me so much time by giving me the order ID and then running everything offline. And then they can send me an email saying, hey, your payment didn't work. You want to update it? And I'll go update it. As simple as that. So anyways, we can read 150-ish pages. Best gift to give to your non-technical boss, because I wrote this book for people who wanted something quick, high level, understand tech very, very well, and give them the edge that 95% developers don't have, and they can read it in a weekend. And now, if you don't have the money for that, the best thing is use a library, because which can happen, right? I didn't have money to buy books when I was there, and I don't want people to spend money to buy my book. So one thing I tell them is, if you ever want to buy this book, take my author discount, because then I don't get any royalties, but the only charge is what the publisher will charge you. But at least you'll learn something new. And then finally, API best practices. I'm going to try to wrap it up in 11 minutes so we can move to the next phase, which is question and answers. Yeah, I got about 11 minutes left, hopefully. So one of the things to understand is that APIs can be done differently. You have gRPC, you have GraphQL, and things like that. But in short, REST APIs will still be there for a long while, because that's kind of the standard. So we're going to talk only about REST APIs today. So one of the mistakes I've seen people make is they do something like get trainings. Well, this is very, very counterintuitive, because what if my verb happens to be post, right? You realize that I could actually do this and also say post. So if I do post here, that doesn't work very well, because it sounds like I have post and post get trainings. That's very counterintuitive. So this one is better, because this does not have any verb. It only has nouns. So let's move on. That's a good idea. Use HTTP verbs and regularly use nouns in your URL. And then what about responses that don't involve resources? In that case, you can translate from English to German, and that's perfectly okay. And in this case, as you can see, I'm using this, right? Which is basically a verb, but that's only if it's an action. Next, as you can see, I've got trainings as well as this. So why only two? Keep it simple. This is not a principle I created, by the way, so don't go to social media and say I said this. This is created by other people. And then this will retrieve all your trainings or multiple trainings, right? If you have a filter. And this will retrieve that one training. It's very, very easy to understand. So something like, look at that. We've got the ID. So if you are giving me the ID, then I'll retrieve only the trainings with that particular ID. And then if you're doing a post, can you believe that it can also create a new training? Yeah, that's very true, because think about this, right? You would have something like an array. So if you have an array and you have training and you said T1, comma, T2, you can pass that array like that. Now, what if you only had one value here, only T1? Well, then the array will still create one training. So, but I just said a little while ago that this is a little interesting, because we said 2 base URLs per resource. So why would you have this? Because that basically is not a good idea. Well, think about this, right? You are saying that the user is allowed to give me an ID. That's not true. This ID needs to come from where? This ID needs to come from, I would say, the database. So the user doesn't really have that info. So why is the user doing this? So in this case, you got to throw an error. And now you're like, well, why do I need to throw an error? Well, if you go back, we've already created 2 base URLs. One is this one, another one is that one. But if you go further and you notice, we've actually done this one for everything. We don't have really this one. But since the user thinks you already had that because you had it on get, it can try to post. So you have to throw an error. So this is not optional. Does that make sense? Now, put means insert. Post means insert, put means update. So when you can bulk update all trainings, assuming you have all the rights and the permissions, you can do that. What about this one? Actually, you can do this because the resource already created. This particular ID is already there. It happens to be 23. And you can updated if it exists, and that's important. Otherwise, it's an error. Make sense? You have to throw an error, because otherwise, if you don't throw an error and the user gets 200, the user might think that the user was able to update that particular training, which is not necessarily true. And then delete, same exact thing. And then remember, right, in this case, what I'm doing is I've got resource not found error, not just any error. And that's interesting, because I'm trying to delete it, and if I didn't find the resource, well, then it's an error. And finally, anything that's required goes in a URL. Required means you have to have this, then it goes here, which basically means trainer number 12 and his or training number 144 for trainer number 12. That's what we're looking for. It's a very easy call to the database. Next thing is trainers 12 and then trainings, and then you have a filter, which is zip equals to this and tech equals to API. So this is all filter, but also remember, this is optional. Anything that's optional, that actually goes in your filter. Does that make sense? It is not anything that's required, because if I go back, anything that's required stays in your URL, and filter starts right here. That's a query string. Error format, this is not very good because it doesn't tell me what my problem was. It says something like authentication issue. And this one is also not very good. I want an error format I can automate and learn from. So an error format is something like this, but also send an HTTP status, right? So make sure you have an HTTP status, and then you have the message, whatever that message is. And then also remember these two, which is basically a code or ID to the docs page, and you send them over there. And it's highly recommended. You see how dig does not have 201. What does 201 mean? Created. So if you create a blog post, if you give me a 200, that means it was a good call, but doesn't tell me if I created something. So you have to make sure you have 201. Dig doesn't even have 304. Well, what does 304 mean? Well, 304 means, something got cached, and I need to know what resources are cached, what resources are not cached. Finally, there's only 3 cases that work. If everything works, that's 200 series. If client did something wrong, that's 400 series. And if API did something wrong, well, then you get an internal server error or 500 series, as you can see. We got 3 minutes. At the minimum, I recommend doing at least what Google does, which is this. But if you don't want to do that and you want to, have a really quick API done, at least these 5 have to be done outside, 200 and 500. Versioning. One of the mistakes I've seen is some kind of date or timestamp on a version. Not a good idea because it's fairly hard for your users to remember and use. Versions should be very, very simple, like 1, 2, and 3. And I would avoid like a decimal number there, because that's like a minor version. And in APIs, you really never have more than 1 or 2 versions of your API anyways in production. It's probably a bad idea to have too many versions. So you can just go 1, 2, 3, 4, 5, and after 20, you can come back and start from 1, 2, 3 again. And this is a bad idea. Can anyone think of why this is a bad idea? Remember what we talked about query string? Anything after that is optional. So what you're saying is your version is optional. And then finally, you've got timestamp, as I said, we just talked about all that. Version is mandatory, remember? And then how many versions to maintain? We said about 3. If it's an API max is 3. And URLs or headers, I mean, it's up to you. URL is easier for your user, so I prefer URL, but there are certain cases where header might make sense too. Pagination. Now, all of this is good. You always have to have pagination, but also remember, you have devices that are different now, right? So you have, let's say you have a phone, or you have a tablet, or you have a desktop, right? So the issue with that is that you can have up to 100 here. What if your users want to see 100 records? That's perfectly fine. on a tablet, maybe max you can go is 50. And maybe on a phone, you may want to go max as 20, right? So you have to have some kind of default pagination, which is device oriented, and you got to think about that. So it's perfectly okay to do whatever you do as long as you include default pagination. And then this is a bad idea because you have hard-coded your type in the URL. That's a bad idea. And this, of course, you are hard-coding, so that's probably not a very good idea either. I would encourage you to do something like this, which is an HTTP header. And then, when you have responses, I would say use the same kind of responses like what JavaScript would have used that. So doc created at sounds better. And of course, they can parse it easily. All right. Well, we finished on time. We have 10 minutes for questions. Thank you so much for having me here. And thank you a lot for the organizers. I understand I've been doing conferences for 15 years. It's a lot of work, and I know how hard it is. So I really thank you for what you've done and giving back to your community. And I'm so glad to be here.
Thank you for being with us today.
We have a question on chat.
Okay, so how can I see the questions? Let's see. Over here. So for the UI part, do you think new frameworks like Angular or React or Vue make us not worry about the rendering? All right, yeah, that's a great question. So, in frameworks also, you have to understand how those frameworks are working out. For example, Angular is a great framework, but if you do not understand change detection and you do not understand how the components render themselves, then a lot of times you may be paying a lot more if you just go by default, what is it, configuration. So for example, if you try change detection, which is push, it's a little different. And then if you have an HTML game, well, how are you putting your components? Now, let's just say you have game as part of the project or the page. Well, then that should be in a completely different component. But maybe you can also have multiple components inside the game because otherwise you may be dropping your frames, right? So yeah, they do help you, which is great. I think Angular is faster than React as well as Vue in a lot of cases, and there's a lot of advantage there. I wouldn't really necessarily say that every framework out there is good because even React, right? Like look at React. They started with React and they used to do Flux, which worked for Facebook, but wasn't a very good idea overall. Then Redux came in. So things change as you go. But if you understand how the basics are, then understand what those frameworks are doing better than others, well, then you have a much better understanding, right? There is never going to be one solution for everything. That's basically like saying for a person with a hammer, everything looks like a nail. So that's why no framework out there will give you every single thing. They'll be good at certain things and other frameworks will be good at certain things. But the benefit now we have is with web components on the same page, I can use, 3 different frameworks by 3 different of these UIs. Now that also creates issues sometimes because it's a lot to download. So you have to have a mix of everything and then of course, use some common sense there. But great question. And I think you're going the right direction. They have a lot of goodness incorporated and they're going to try to keep making it better as they go. For the microservices part, do you have some reference to just a good microservices architecture? And can you explain load balancer? Oh, okay. So the microservices part, right? So the issue with microservices is that, first of all, you have to have a real need for microservices. If you are going to do, let's say, 10 nodes total services wise, you're just better off creating monolith services that can talk to each other and don't have to go through the entire Docker, Kubernetes, Terraform piece of it. But if you really are building something that's going to have to scale quite a bit, and your major reason is being able to deploy separately, good security, right, things like that, and you may get into hundreds of these containers. Well, in that case, microservices might make sense. Now, just remember, if you do monolith well, correctly, interestingly, monolith is actually faster than microservices. There is a reason. The reason is that microservices will never be able to get you to micro, or maybe down the line in a while, but not necessarily. But microsecond response time is extremely hard because think about this, right? You're going to make a lot of hops. So you're going from one process to other process, whereas in one monolith, if done correctly and done with high performance, it's going to be faster because everything is in memory versus going to a different process that's out of process. So first thing is understand that you really have a business use case, not doing it for resume driven development, which a lot of developers do. In that case, now microservices becomes important for you. So instead of thinking of a pattern, think of this as, how do I use all principles? What's the difference between principles and patterns? Principles are always the same. So if I use a distributed programming principle, it really doesn't matter to me if I'm using now with, let's say, Node.js or .NET or Java. The principle will apply everywhere. Pattern to me is solving one particular problem. So let's say use the strategy pattern. It solves a problem, and decorator pattern solves another problem. But you'll be surprised that strategy pattern will never say solve the same problem as decorator pattern. But you realize the principle between the two is the same: abstraction. And if you can abstract, well, abstract well, and that's exactly the principle between both the patterns. So in microservices, there's a lot of patterns that are out there. But if you understand the principles of distributed programming, who cares about the patterns necessarily? It's good to know those patterns, and then you simply apply the principles, and you will be in a good spot, right? Because otherwise, I may give you a pattern today, but that may not be the best for your use case. But there's a lot of different patterns that are out there, right? Things are event driven, but I mean, like, of course, that's a good idea, but might not work necessarily for your use case, right? There's an actor model that is a great idea for a lot of different problems, but may not necessarily work for your use case. Until I know your use case, I would not really answer that question with a pattern, and that's what I would do. And load balancer is very simple. Basically, the point is, if people are making a call to your website, they're really not making a call to your servers, right? They're making a call to a load balancer at the end of the day, if you have one, because the point of the load balancer is to see which server is, better to take the next request. So let's say, you have 10 servers and all of them are 67% utilized, and another server is 23% utilized. It's better to have a load balancer because it looks at the load and goes, oh, that one's only 23% utilized. Let me send a bunch of calls there. Now, while that server becomes 75% utilized, another server is down to 65. So now you have the load balancer that takes care of that load over there, right? So now someone said Node is better at scaling. That's not at all true, by the way. I'm going to send a message back here, right? So .NET Core, .NET 6. You will be shocked to believe this. Actually, let me just show a screen there. So you see, you got to always do your own research. Do not listen to people who blog out there, because they are paid to blog and they will say whatever they want to say. I hope you can see my screen, right? So Tech Empower. Benchmarks. If I were to go to Tech Empower benchmarks and look at the data, look at that. ASP.NET Core can handle 7 million requests. That's on the same server where Node.js can only handle 665,000 requests. That's more than 10 times slower. Look at the rank, it's 173. And ASP.NET Core, which is .NET 6, basically handles 7 million requests when Node.js only handles 600,000 requests, or 665,000. More than 10 times worse, right? So see, Node is better at scaling. Prove to me how. So I've heard that .NET is much better than Node.js performance-wise, but Node is better at scaling, right? So this is the thing, right? You got to understand that question is good, but always understand what are you trying to do. In certain cases, some technologies are better, certain cases, other technologies are better, and there's a big difference. But in this case, performance computation-wise, .NET was always going to be better because it uses multiple cores, which Node had a really hard time with. Node started with one core. Node was good at I/O scaling. It wasn't the best at scaling. It was actually good at I/O scaling. Because if you had to scale computation-intensive jobs, Node would never work. It was always one thread, and that thread would be stuck forever. Try doing, let's say, Fibonacci or 5,000 on Node, It might take a few seconds. And if it does take a few seconds, what happens to other calls? They all get stuck, right? So after some time, .NET actually also got better at I/O. So there's a huge advantage there. But still, when you look at JSON serialization, I mean, there are other frameworks that are actually better than .NET 5, but in .NET 6, they made a lot of improvements. So things keep changing all the time. There's no necessarily one best framework, but I think .NET is a pretty amazing framework. And, in certain cases, we use Node, and it's not a bad framework either. So we got 30 seconds left. Any other questions?
Okay, thank you, Sander. We are run out of time for questions. It's time to announce winner. But thank you very much for attending us today, and we really enjoyed here in Tripoli, Lebanon, in your session. And we hope to see you very soon in future events, and maybe in Lebanon one day. Thank you.
That will be great. Love to visit you guys, all of you. Thank you so much. Have a great day. Take
Okay,
care.
say goodbye to the speaker.
Thank you. Oh wow! Can I have a picture of all of them?
Wow.
If you don't mind, send me a picture. It is an amazing group of people. Thank you so much, everyone. Love you all. Thank you. Bye bye.